Welcome everyone to the afternoon session. The first speaker of the afternoon session is Professor Arvind Nair from TIFR Mumbai. He's going to speak on automorphic Lefschetz properties and L values.
Okay. Thanks to the organizers for inviting me to this conference. And I've already been enjoying the talks. I wasn't able to be here last week, but I've heard that the talks were very good. They've been nice. Okay, so as I said, my title is something about automorphic Lefschetz properties. So I'll be talking about modular varieties of various, of a specific type. But what I'll have to say is kind of not interesting in the case of modular curves. So a bit disjoint from what at least the title of this program is. But these are, of course, the natural higher dimensional generalizations. So the basic setup that we have, and I should say that what I'm going to say is, part of it is joint work with, I'll just say, is part of it is joint work with Ankit Rai, who's now at CMI. And part of it is based on discussions and ongoing discussions with Deependra Prasad, who is not from TIFR. So, but I should say that most of the theorems will be in the part that that is with Ankit. And in fact, I should apologize because this is already a couple of years old. It's so old that it's actually appeared. So, unlike it's not hot from the press. But I want to talk about how some of the results we prove can be put in the framework of branching laws. I'll say a little bit about it at the end, and that's an ongoing sort of thing that we're discussing with each other. Okay, so what is the basic setup? The basic setup is we're interested in modular varieties. So these are varieties of the form quotient of a discrete group by a discrete arithmetic group. So I'll assume gamma is congruence. And D is a symmetric space. So there is, of course, already a dichotomy. Either it's Hermitian, that is, it has a complex structure, or it is not, let's say. And some of the results will apply to only Hermitian cases, and some of the results apply to some other cases which seem to behave as if they're Hermitian. Okay. So this is the basic setup. I have a congruent subgroup. D itself comes from a reductive or, let's say, semi-simple algebraic group. It's the symmetric space of maximal compact subgroups, or the quotient. Okay. And we're primarily interested, okay, so what are the cases where, so there's a Lefschetz in the title, so there must be a divisor somewhere. So, or at least a hyperplane or something, maybe. So what are the cases? We're primarily interested in the following cases, which is that the non-compact, the real group is SU1n-1. So of course, that means we're taking some sort of form of it, and then we're taking congruent subgroups in that, and sitting inside SU1n. Okay, so I'll say more precisely what one wants to do exactly. And the other cases are where you have SO2n-1 sitting in SO2. So what am I saying here? So you start with the Q, let's say this is G, and this is H. And this again is another pair GH. This is a second example. So G is a rational form of it's a rational algebraic group whose real points, maybe not exactly SU1n, but we'll allow ourselves to take that so let's say the non-compact points, part of the real points, the product of the non-compact factors of the real points is SU1n or SO2n. So the point is that these are the two cases, and we're really only interested in n at least, I guess, n at least 2, but let's say we can even assume 3. Yeah. So these are really the only interesting cases in which you have a modular variety, which comes from this group or this group, which contains a modular subvariety. Okay, so I'll say exactly what this happens. So if G, H are Q groups, so let's say I have a homomorphism. Giving these inclusions on non-compact real points. So then when I take the subvariety, say corresponding or intersected gamma with H, so let me just assume this is an inclusion, so that's not simple. If I look at the symmetric space of H, it maps into the symmetric space of G, and I get a morphism like this, which is finite over its image, and the image is a divisor. I mean, I'm saying something obvious, but this is basically the only situation where this happens. Okay, a complex divisor. So in some situations, the natural question is, well, so you have, okay, so this is a fact, which we'll assume all these facts. So in the Hermitian case, I should have said this, that M is a quasi-projective variety. Okay, just like modular curves have, if you define them as complex manifolds or complex analytic spaces, they get an algebraic structure. It's a general theorem from the 60s of Bailey and Borel that these quotients like this, if the symmetric space has a complex structure, are actually algebraic variety. And so that's what I meant when I say it's a complex divisor, it's a co-dimensional one. So, well, the immediate question is, well, the silly question is this an ample divisor? Okay, let's assume for the moment that everything is compact. That is not just quasi-projective, but projective. And it's fairly easy to say that that's unlikely to be true. But the question is, can you take finitely many of these? The sum with coefficients if necessary. Sorry, the linear combination, that's what I see. So I'm choosing different subgroups H, yeah? So I won't, so MHs, let's say. And can one take a finite, is some finite linear combination of these an ample divisor? Okay, and let me now just for later this thing set up what I want to say is that in the quasi-projective, I want to treat projective and quasi-projective cases uniformly. In fact, I mean, the main new things that I'm going to talk about is actually to do with that, right? So it's well known that in the cases where where these are non-compact quotients, like modular curves, there is a canonical compactification, which is a direct analog of, which is an analog of the cusp compactification of modular curves. Okay, so there exists in general, there exists an extension of, I should give this a name, maybe phi, an extension of this to come to projective varieties, projective compactifications. So I'm talking about here about the canonical projective compactifications. I mean, there are many ways to compactify, but the point is these have a canonical one. And then you can ask the same question, is some finite linear combination of these images of translates of this an ample divisor? Now, when I want to take different Q groups, I might as well just basically take one of them, that is H sitting inside G, and then take its conjugates under elements of G which are rational. Okay? And if you think about it a little bit, that becomes the question, is some finite linear combination? I mean, I guess finite is probably unnecessary to say here. Of Hecker translates. Okay, so basically I have this divisor, I translate it around using the Hecker operators of G, and I ask, is some finite linear combination of Hecker translates of this thing an ample divisor? Okay, so this is certainly, as far as I know, it's not known. I mean, it's almost very likely to be true, but the whole point of this thing is that one can't prove this, right, directly. So there are a number of, I mean, I have to be careful about what I mean by exactly can't prove this. I'll say that one can prove it in some version of it. But if this were true, what would this suggest? Then the classical Lefschetz theorem tells you that restriction in cohomology to an ample divisor is injective. Okay? So since we're allowing a linear combination here, it only makes sense to consider the injectivity of the restriction map, not the surjectivity, because we're going to allow more and more translates are allowed. So an immediate consequence of this would be that at least in these instances, the Ullbach map in cohomology is injective in degrees up to the middle dimension. So a consequence would be, okay, so that this map to that finite sum. So I'll just write it this way. Okay, so I've taken a finite number of Hecker operators, and each of these is phi star, but then I have also composed it with maybe I have first applied some Hecker operator. So I'll make my notation more clear in a moment if there's time. And I sum these maps, and there's a finite sum of these such that this becomes injective in degrees. Let's just make it n minus 1. That's the dimension of H. Okay. So this is the sort of thing that one has in mind when one talks about an automorphic Lefschetz property, is proving something like this. This is a consequence of this statement. Now, I've been a little careless because I rewrote this statement as there are really two questions here. One is question and one is maybe question star. The question is where for the open varieties or compact varieties if they were already compact. And question star is for these singular compactifications. So these are singular. So an example is, well, except for the modular curve example, but I've taken n at least 2. Okay. So as soon as n is at least 2, the modular variety of this, the canonical compactification is singular, and the same is true here. In fact, the only case where a modular variety's canonical compactification is smooth is the modular curve. So it's a bit unclear whether this consequence would follow from the statement, or what exactly this consequence probably would follow. Not exactly, but it's a bit unclear what exactly this will give you if you could prove this, but it would give you the optimal thing one has to believe. Okay. So this question is not, as far as I know, understood. So, but there are many results about this kind of thing. So let me just state that I'm going to state some results and I'll attribute them. But property questions of this kind have been worked on by a number of mathematicians. So I'll just recite a list, and some subset of them will get cited again. So I think questions like this were first considered by Oda, then Weishauer, Murthy, Ramakrishnan. Arthur wrote an influential paper where he raised some questions of this type. Harris and Lee, Michael Harris and Janshu Lee, Closel, Venkatramana, Rajan, Michael Harris, so I have him twice in the list, and Bergeron and Closel. Okay, so some of these results will be mentioned again. Okay, so the answer is that in many instances this can be established. So let me state a theorem and maybe. Okay, perhaps a simple example would be in order here, just to see the flavor of what's going on here. Suppose we look at H1, so an example. So this is the original example of Oda in 1981, which sort of started people looking at these kind of maps, which is that suppose I take the situation SU1 n minus 1 sitting inside SU1. Okay, so the corresponding inclusion on the level of bounded symmetric domains is This is an inclusion, and then when I go modulo these groups, it becomes a finite map over a subvariety. And this thing is an n ball, complex n ball. And this is an n-1 ball. Now look at the restriction in degree I equal to 1. So this is a complex manifold. So H1 has a direct sum decomposition H10 plus H01. Okay. And just so does this. And so by kind of Hodge symmetry, if you prove injectivity on either one of these, it follows that it's injective on the whole thing. Okay. So what is H10? It's the space of holomorphic forms on this object, right? One forms. Now, it's very easy to check if a holomorphic one form vanishes along on the cotangent space or on the tangent space of this variety, because you know very explicitly what the tangent space here embedded in that is. So it's just one, asking it whether it vanishes along a codimensional one. But on the other hand, I'm allowing myself lots of Hecker translates. So basically, a holomorphic form, one form cannot vanish on too many different translates, rational translates of one subvariety. That's subspace. That's obvious. Okay. I have at least, I have enough subspaces. I can translate it around using the group. So it has to do with the actual embedding of how the tangent spaces are related, but it's a very elementary calculation. Okay, so Oda's original example was non-compact, so you have to make an extra argument to get rid of the issue that H1 is non-compact, but actually it turns out H1 is the same for this guy and any smooth compactification. So it's a very simple principle that says that now if you try to restrict to any sufficiently many Hecker translates, it can't be non-zero. And then by Hodge symmetry, it's gone. So this is a very simple argument, but it doesn't seem like simple arguments suffice in any other cases. Okay, so there is one more important case, which is somehow not complex, but I'll just write it down here. It will come up in the main theorem, which sort of again behaves like a divisor. So here the point is that the symmetric space of this guy is this is a real hyperbolic manifold of dimension n. This is a hyperbolic submanifold of dimension n-1. And so the real dimensions are n and n-1. And it's a observation which I'll mention. Well, when I state the theorem. So somehow the point is that these things are actually closely related to SO2n, at least in what I'm going to say. And that's somehow why automorphic Lefschetz properties hold in greater generality than one might think. Okay, so just to introduce some notation, let me introduce just a notation because it simplifies things a bit. Okay, so so now for, say I have group G, I have M gamma, which is gamma modulo G mod K or D, okay? And I'm just going to look at I'll give a name to this module, HIM, as being the direct limit of HI over all congruence gamma. Okay. And now I'm giving myself a subgroup H. And so it's clear that I have a map like this, the corresponding guy for H. Okay, I won't write what this is. It's obvious, right? So the advantage here is that once you make this into this thing, you have sort of the rational group acts here, and the rational group of H acts here. Okay, and this is obviously, so this action, if you think about it, it's conjugating gamma, and that is really the action by Hecker correspondences. It's just that we're considering it in the limit. So it's just, this is the action by Hecker correspondences. So it's convenient to do the following. Okay, so either by Frobenius reciprocity or just by some explicit thing, we introduce the following induced module. I'll just define it and then it'll be clear what is intended. Okay, so let me just write this down. So these are, as induced modules really are. This is a function space, functions from that to that, which have a right transformation property according to F. And F is invariant. Okay, so these are functions from GQ to U, which are invariant. Each is invariant under a certain congruence gamma, and it has a right transformation property with respect to H. So the point is that this map just becomes, therefore, gives you a map, which we'll call big res from HIM to this induced module. Okay, and res alpha not equal to 0 for any alpha is essentially equivalent to saying there exists a Hecker operator so when I apply the double coset to alpha and then I restrict to MH, this is non-zero. Okay, so it's just a cleaner way of packaging this statement. So the automorphic, it's exactly a way of repackaging this statement. And the automorphic Lefschetz property would be saying that this map is injected. Okay, maybe I shouldn't have introduced this because it doesn't really do much of a role in what happens. Okay, so having said that, let me say the theorem. I'll state which parts of it are due to whom. I'll separate the compact and the non-compact cases. Let's say in I less than or equal to n, which is say the dimension of MH as a real manifold by 2 in all cases. So what are my cases? I'll just enumerate them again. SO1n minus 1. Sitting inside SO1n. SU1n minus 1 sitting inside SU1n. And 3 SO2n minus 1 sitting inside SO. Okay, so the point is that, okay, the first one is, so these two are essentially what one would expect if this question had a positive answer. Okay, that's 2 and 3. And one is this somehow hyperbolic things behaving like as if they were algebraic varieties of half the dimension. Okay, so, and in the non-compact cases, this is true for I less than or equal to the dimension. So I'm using real dimensions here so that everything works out correctly. Just stating the theorem so that. Okay. Okay. So I have to, so let me state the theorem and then I'll say who proved what. So it's basically saying you have an optimal Lefschetz property in the compact cases. Okay. So just, I hope everybody's familiar that there are ways to produce higher dimensional compact hyperbolic arithmetic congruence manifolds. There are the complex versions, and then these are Shimura varieties of type 2, n. You have to start with a totally real field, and you take so for example here, you would take a totally real field, you take a quadratic form which had a certain signature at this signature at one real place, and at the other real places was definite. And that would give you a real group whose non-compact part is like this, right? You throw away the compact factors, and then the corresponding congruence quotients would be compact. Over Q, for example, if you have enough variables, maybe n is 4 or 5 or something like that, every quadratic form actually comes from a split quadratic form. So it can never be compact. I'll come back to that case. So somehow this is in some ways a generic case over Q. Okay, so this theorem this was proved by Bergeron and Clausel around 2013. These two were proved by Venkatramana a little earlier. So I should say that I'll say some more about this. This is kind of this version in the non-compact case is a little, so it's the Bergeron-Clausel argument plus some more. And this, the case 2, that is complex Ball quotients and injectivity and restriction. So the thing to note is that there is a loss of dimension. Of course, I'll come back to that. This was proved by me in 2017 and also by Bergeron and Clausel. They gave a different proof soon after. And this is by Ankit Rai and myself. And this was proved a couple of years ago or two, maybe, yeah. But you could say, since it's just appeared, we can say it's 2023. So it looks wrong. Okay, so this is the sort of summary that with great difficulty one proves the consequences of this stuff, this fact, which is geometrically certainly ought to be true. Yeah. So I should mention something about the methods. So there are three types of methods, let's say. Okay, so maybe since I should advertise a case where the theorem is interesting and new. So example, if G is the special orthogonal group of a quadratic form Q, where Q is a quadratic form over Q in at least, let's say, 6 or 7 variables, maybe. Let's make it 10, safety. And H is the special orthogonal group of Q restricted to a non-degenerate subspace. Then this theorem 3 is a new theorem. Then 3 is true. Okay, so this is a new example, you might say. Okay, so I should say that this includes at least some moduli spaces, which some spaces one might care about, which is, for example, the moduli spaces of polarized K3 surfaces correspond to modular variety of the type SO219. And this tells you that the restriction in cohomology to certain subvarieties, which sometimes can be given moduli descriptions, is injective up to the dimension, but with a loss of 1 degree. Potentially, yeah. Okay, so the remark. So there are 3 types of methods. Okay, so very broadly, all these methods are Hodge theory of some kind. So they're either analytic Hodge theory in terms of automorphic forms, or they are, but more than that, there's some arithmetic also, or they are Hodge theory of algebraic geometric type, but they significantly include mixed Hodge theory also, or they are somehow related to cohomology again. So let me just say what the 3 types of arguments are. One is so this is the Berger-Shaunak method. So I'm getting tired of writing Bergeron and Clausel, so I'll just write BC. Okay, so I should say that this statement, the one proved by Venkatramana, was conjectured by Harris and Lee a little bit before, and that in the compact cases that you would have this Lefschetz property. And I think they started applying the Berger-Shaunak method, whatever that is. So maybe one should call it the Berger-Shaunak-Harris-Lee method. And I guess their idea was that if you knew enough about automorphic methods, you could prove this, but Venki gave a nice, very clean and nice geometric argument. Okay, for those cases. So that is for the complex cases. So I should say that he basically answers this question not this way, but on the level of cohomology. Yeah. So he shows that you can take Hecker translates of the class of the divisor in cohomology, and it will be a certain ample class. Okay, so I shouldn't have digressed. So Bergeron and Clausel developed the Bourgassard-Nack method and applied it to this case, and it was their observation or discovery that these cases orthogonal cases should also have Lefschetz properties. And this thing uses a lot in the sense that the reason this was finally, I think it started in the early 2000s, but it culminated here because Arthur's endoscopic classification became available. Okay, so that depends on a lot of things, including the fundamental lemma. So I have to say some here that I should exclude, in this case, I have to exclude triality forms, or they have to exclude triality forms of D8, of SO8. It is a really technical point, but it has to be excluded. Whether it doesn't seem likely that it should be. An essential thing is just that they're using results of Arthur, which have to exclude that at the moment. At that time, I think still. So that is the three types. The second type is the argument I mentioned, an argument by Venkatramana in the Shimura variety cases, or the modular variety cases. And the third thing is, okay, so these two would cover the compact cases, but if you was interested in the non-compact cases, you need, in addition to these two, and somehow it's not just that you're able to use these two things. You use this idea, you use this idea, and you have to do a lot of, and then they build up something. So maybe non-compact cases require 1 plus 2 plus mixed Hodge theory. Okay, so for singular varieties. So given some time, I'll say something more about that. So in some sense, we use the whole package of weights and the decomposition theorem and all that in some way or the other, right? Okay, when I say that's Ankit and me, right? Okay, so this is the thing. So what about the missing degree? So there are two reasons that this is unsatisfactory, perhaps, at least 2 reasons. Just a second. Okay, so I'll come back to time permitting. I think I'll come back to somehow at least some part of the essentially new argument here, just so it will show both how the missing degree, how injectivity is lost in 1 degree, but it will also show how that is a subtle question actually. Okay. Right. Right. Okay. So yeah, so there are several things involved in that. I think that, sorry, just a minute. Okay. So what happens in degree? So this is a remark about. So the way I've written it, it's the real dimension of MH over 2, which is equal to n in the algebraic cases. That is SU1n minus 1 and SU1n and SO2n minus 1 and SO2n. So what happens is related to the fact that there exists. So the point is one can construct classes in, let's say, okay, so we're only interested in classes in degrees below, so sorry, somebody should have been, n is actually, the subvariety has dimension n minus 1, not n, right? So this is also n minus 1. So that MH over 2 is the right formulation. Okay. right? So here the point is that one is looking at cohomology for, let's say, M in degree n minus 1 and cohomology for degree mh in degree n minus 1. Okay. So now here, this is the middle dimension for mh. And this is one less than the middle dimension for this thing. Okay. So the point is one can construct classes in the larger variety in this degree using Eisenstein series. Okay. And okay, so what I'm saying is true in a particular example. For example, if depending on, so the existence depending on something, a condition, something like L half chi not equal to 0, where chi is in a quadratic imaginary character. Sorry, equal to 0. Okay. So suppose, for example, you take a standard Hermitian form of type with respect to an imaginary quadratic field of extension of Q, and you look at that group, then there are ways this has parabolic subgroups, and you can construct Eisenstein homology classes corresponding to this condition, if this is true. Okay. So these are residual Eisenstein classes. I won't go into the details, but these are residual Eisenstein classes. However, yeah. And then the question of whether they restrict non-trivially here, or after applying a Heck operator, they restrict non-trivially here, is quite subtle, because this tends to have in that degree only cuspidal homology. So one has to sort of say that this Eisenstein cohomology class restricted and paired against some cuspidal cohomology class is non-zero. So one expects that this is some sort of I don't know, Rankin-Selberg type condition. Okay. So the point is that I'll explain in a moment. I'll go into these geometric arguments we give here, and it'll be clear why the geometric argument doesn't work at all. So this seems to be okay. So okay, so let me state one more theorem just for completeness. And okay, so this again, this is in the compact case, it's due to Bergeron and Clausel, and the non-compact case is ours. Suppose corresponds to so one looks at sort of a mixed restriction from a complex hyperbolic manifold to a real hyperbolic manifold. And let's assume that n is at least 3. Okay. Then okay, and in the compact case, one H is not triality or something. Okay, whatever that means, right? Some technical condition. Then what happens is that you can restrict a class, but not an arbitrary class, but on the larger variety, you can restrict a class of type I0. So that is like a holomorphic class, right? And you can, that same induction game works for this map also. And this is injective. I less than equal to n over 2. Okay, so this is the compact case was proved by Bergeron and Clausel, and non-compact is in. Okay, so let me emphasize again what this means. This means I take a class of type I0, and it may not vanish when I restricted cohomologically. It may vanish when I restricted cohomologically, but I can always apply a Heck operator and get a non-zero. Okay, and this, you know, again, once the thing is set up, it just turns out our arguments can, you can come. This is much easier in the sense that you can just put two things together. It's not like the proof of this case here, where sort of everything is kind of interwoven. Okay. Okay, so one more remark I want to make is that in this case, sorry, where's the main theorem? Yeah. So notice that there was no loss of degrees in the hyperbolic case, right? The real hyperbolic case, yeah? Whereas there was this loss of degrees. So this is not an accident in the sense that, of course, I mentioned here that what causes the loss of degrees is related to the vanishing of an L value. And the point is that there is no, okay, so this is just some philosophy, is that the behavior of L functions, the way it influences the cohomology, elaborate through Eisenstein series construction, it ends up causing some mixedness in some degree. So what sort of happens here is that this class causes a mixed thing to appear in Hn. So I should have said, for those who are familiar with these things, that in the degrees we're interested in, the cohomology of all these varieties is pure. Okay, so that's okay. But this is the degree we're interested in, the maximal degree. In 1 degree higher, it becomes mixed because of this. And that somehow has an influence on the restriction in the lower degree. It doesn't have an influence directly on the lower degree, but it has an influence on this restriction question. So, and the same kind of thing certainly holds for SO2n-1, except the same situation is much more complicated, but that's the point. So what I'm trying to say is that this loss of a degree is is related to some slightly subtle issues. And those issues are not there for the orthogonal case. There's somehow no motivic or algebrogeometric object anywhere. And so that difficulty goes away. Okay, so let me spend a few minutes discussing, okay, so the proof is fairly dull, but okay. Okay, so let me just say, so let's consider the case 3, okay? So I take, since that's the most complicated case, we should consider it now. So I take, and I assume that the Q rank of both groups is 2. So I just take, okay? And so then I have this MH, and it's more or less sitting as a subvariety in M. And then I compactify it, okay? Now, in this canonical compactification, what happens is that MH adds a bunch of modular curves and their cusps. I mean, these are open modular curves and their cusps. And when you play the same game for the bigger group also, the same thing happens. Okay, so this Satake-Bailey-Borel, as it's called, compactification behaves this way. And the modular curves are related to the isotropic subspaces of rank 1, and then the cusps are related to the isotropic subspaces of rank 2, right? So you get a map like this, right? Now, I wrote this arrow. It's true that the map phi from these two extends canonically to that. I said that earlier. Okay. So the natural thing is to just try the most naive thing, break this up, use exact sequences that for the interior and the boundary. And kind of that works, but there is some tricky things happen in this particular case. So I'll just write down what one does. So there are subspaces. So maybe I'll formulate. There are subspaces, or there is a filtration of the cohomology in degree of HM. And this is true also for H, yeah, which is of the following form. So first one takes I'll explain what this is. Okay, and then this one is the tricky one. Okay, so what you want eventually to sort of attack this thing, right? And what you want to do is you filter this thing. Okay, so this is the image of the compactly supported cohomology. Okay, And this is a functorial object because phi is a proper map. So there is a similar filtration for H. This is a functorial object. So you get maps, you get the similar filtration for H and you get maps on. This is a sort of tricky group that one has introduced. So you take, what you do is this is like considering, okay, I can't, it's just drawing a picture here. So this is my MH or M. These are the modular curves and these are their cusps. There are more of them. And what you do is you consider the cohomology of this object where I add the modular curves, but then I put support conditions, compact support towards the boundary. Now that's a very obvious thing to do. But the tricky part is that then you have to take this weight graded piece. Okay, so, and the point is that this is neither pure of one, this is not pure of weight I, this is neither a quotient nor a sub, it's just the right subspace. Okay, I won't say why. So this, but because of, weights are functorial, so this will be functorial. So there's a similar diagram of spaces for H, and one basically climbs up the diagram and whose injectivity here, here, and then here by analyzing what the difference is in these things. That's a one-line summary. But introducing this space this is essential. So there are a number of tricky points of, I shouldn't say they're obvious ones. Yeah. Okay, so I think the expression is that you write this down and then follow your notes. Okay, so where does the injectivity fail? Okay, so just to understand that in the SU1N cases, there are no modular curves. The compactification is just the cusp compactification. And this two-step thing is not there. And you just have to analyze what happens at one step. Yeah. And that involves understanding what happens at infinity. The boundary is all well understood. There are very nice classical results about it. And what happens is that why does it fail? These classes that you would produce here, if you were to look at it, so let me just write down, you would be producing classes here, which are forced to die under a certain map to the other guy, the boundary in the other guy, but they might survive in the cuspidal part. So this is what I was saying, where you have to look at these classes and somehow they need to pair with a cuspidal class on the subarray. Okay. So, okay. One more important point is that an essential input in the second step, so climbing up this tower, so that is dealing with the cusps, is that one has to use the theorem of Bergeron and Clauzel from the compact part for the special orthogonal group. So what I'm trying to say is that right, okay, so maybe I should say this way. The injectivity on this is proved by adapting Venkatraman's argument. The injectivity on this first difference is proved by adapting another argument of mine from the unitary case. And then to go to this next step, one has to combine some arguments involving weights and the compact special orthogonal case. Okay, so the point is that the compact special orthogonal case is somehow appearing as a local, not quite fundamental group, but it's appearing as a quotient, subquotient of the local fundamental group at these singular points. So what this shows very clearly is actually the orthogonal case is kind of still an algebraic setup in the sense that if it's sort of a local, what one is using is like a local Lefschetz property for those algebraic varieties. So in principle, it should be possible to, if one could answer this question directly, okay, this is not a theorem, but I'm fairly sure it's true. One could answer Q star correctly directly, one would actually get all these results, including the special orthogonal thing, which I remind you depended on Arthur's endoscopic classification. So it's fairly deep. Okay, so how could one hope to attack questions Q star? I have no idea. Yeah, of course, I think I'll just say, famously, Borcherds constructed automorphic forms on special orthogonal groups SO2Ns with singularities along SO2N minus ones. And in some very special cases, one can identify those as showing that something maybe as some combination of those devices is ample. So it doesn't seem like an impossible thing to directly answer that question. Okay, so finally, let me say that these are all cases of somehow related to the BGG, sorry, not BG, GGP philosophy. So Gyan Gross Prasad, restriction laws. Moreover, that framework actually suggests some new questions. Yeah. So, for example, one could even in the classical case, one could ask something like, let's just look at this, this basic map that we have here. And one is asking a question of the form, suppose I have, so this is the inverse limit. So this is a GQ. Let's move over to the Adels for a moment. And I have a GAF action, and suppose everything is semi-simple, etc. And I have pi1f here that appears here. And suppose one has a pi2 or pi h, let's say call this pi g and pi h. And suppose one knows something like this, that this is a quotient. Can one embed this situation in, and suppose cohomological? Yeah, no, can one embed this in that situation? So, okay, so that means can one find a cohomological representation, which when you, I didn't say what those are, but it doesn't matter. When you tensor it with this, it appears in space of Automorphic form. Similarly here, the cohomological representations are related as in the Burger-Sarnak method. And then one would want to say that this is related to some global non-vanishing period. So, and deduce that this can be true. Only if there is some global non-vanishing period. Okay, so it'll take me too far afield to say anything about this. Okay, and it seems quite possible that one can say something about this general question and reduce it to that. The other thing which is nice to think about branching laws is that maybe it'll explain what exactly, yeah, so as I said, it's not totally clear what should happen in the case in that missing degree. So a certain vanishing condition will produce classes, and then it appears that for those classes to survive, there has to be some non-vanishing of some Rankin-Selberg type L function. It would be nice if that fits in well with this thing. At the moment, it's unclear because, well, we haven't done all the calculations. So, okay, I think I finished a bit early, but do you have anything else to say about this? Okay, I think I'll stop there.
Any questions? Comments?
Yeah. Yeah. No, these are too somehow soft. So, I mean, these are not precise enough for that. So one, I would rather see that something that you could prove using, it might be that you can prove something. For example, I mean, what I said earlier, right? Watchers might tell you how to write down something, which will answer question star, and then this would follow by standard method. Yeah, but it's definitely weaker. Yeah, it's definitely weaker. In this context, there is something to be said about if one could refine the restriction to a GGP type restriction, then you might be saying specific things about a certain period interval. Of course, you know, because the non-vanishing of GGP period intervals has been refined to a prediction about the value at half and all that, Ichino Ikeda type things. But I don't think these are very soft methods. I don't think they'll prove something about that. Doubtful. Yeah. No, I don't have any application of that. Yeah. It's just something that seems odd, but that means that there are certain submoduli which you can translate around and which carry the full co-module. Which I don't know if it's, I don't know. Potentially this might be useful actually. Even H2, I think it tells you something perhaps. Yeah. That's right. Yeah, that's very, very subtle stuff. Yeah.
Any more questions? If there is none, let's thank the speaker again.